Hi, welcome to the lecture series on frequency domain analysis. In this video, we are going to look at three different problems on frequency domain analysis, especially on frequency domain specifications. So I've taken up three problems for this session. The first problem has got three subdivisions. And in the first subdivision, we will see how to find out the steady state response for a sinusoidal input given the forward path transfer function of an unity feedback system. And the subdivisions 2 and 3 deal with calculating the frequency domain specifications if the forward path transfer function of the unity feedback system is given. And of course, we'll be calculating it for different gain values. The problem 2 is on correlation between the time domain specification and the frequency domain specifications. And the problem 3 is on calculating the gain crossover frequency, phase crossover frequency, gain margin, and phase margin. The theoretical concepts on these problems have been dealt in lectures 1, 2, and 3 of frequency domain analysis. So I would recommend you to watch those three videos before this one. So let us start with the first problem. So in this problem, a closed loop unity feedback system is given and its forward path transfer function is also given. So what we need to find is the steady state response for a sinusoidal input. If you look at this input, it has got two components and both the components are sinusoidal in nature. And you have to find it for a gain k value of 5. And the second and third divisions of the problem is to calculate the frequency domain specifications such as resonant frequency, resonant peak, and bandwidth. And you have to calculate for two different values of gain, that is 5 and 100. So since we are being given an unity feedback system, closed loop system, see all these things, whatever we need to calculate is for the closed loop system. So therefore it is necessary to find out the closed loop transfer function of the system. Closed loop transfer function means that is y of s by r of s. We know that the closed loop transfer function y of s by r of s is equal to g of s by 1 plus g of s into h of s. So let me say the closed loop transfer function is t of s. So this is what I said. And now if we substitute the value of g of s, that is the expression for g of s, this is what you will get. Please note that since this is a unity feedback system, h of s has to be taken as 1. And this is what you will get on simplification of this expression. So we need to calculate all these things for values of k and 100. And let us find out the transfer function for the values of k equal to 5 as well as 100. So you can just substitute the value of k by 5 first. And also to calculate this resonant peak, resonant frequency and bandwidth, we need the damping ratio, that is the zeta value. So how we can find out the zeta value? So we need to equate this or compare this with the prototype second order system. Prototype second order system's transfer function is omega n square by x square plus 2 zeta n omega n plus omega n square. So if you compare, omega n square is equal to 5 and 2 zeta omega n is equal to 6. So if you do those comparisons and do some simplifications, of course, you should be familiar with this in time domain analysis, so I'm not doing it. Anyhow, you can directly get omega n as root of 5, and it is 2.236 radians per second, and theta is equal to 1.3416. And similarly, we can find for k is equal to 100 also. So this is what we get for k is equal to 100. In the same way, we can compare with the prototype second order system, and omega n we find that 10 radians per second, and the damping ratio theta as 0.3. So we will move on to the first subdivision. So in the first subdivision, we need to find out the steady state response for the input. So as I said, that input has got two components. Both are sinusoidal in nature. Let me call the first component as R1 of t and the second component as R2 of t. So this is what R1 of t is equal to sine t plus 10 degrees, and R2 is equal to cos 3t. So it should be noted that these two have different frequencies. Okay. So if I compare the first component to sine omega t plus phi, then omega is equal to 1, and therefore omega 1, let me take the frequency of the first component as omega 1, and it is equal to 1 radians per second. Whereas the second component cos 3t, when compared to cos omega t, see the frequency omega is equal to 3 radians per second. Let me take its frequency as omega 2, therefore omega 2 is equal to 3 radians per second. So let me take the components of the input one by one. Let me take the first component, that is sine t plus 10 degrees. And if I give only this input to the system, then the output is going to be, the same sine t plus 10 degrees with two changes. That is, one change is the magnitude and another change at the phase angle. What is it? How is the change in the magnitude? The change in the magnitude, it is multiplied by the g of j omega magnitude, and the angle of g of j omega is added to the phase of this input. So in the same way, if I take the second input, that also is going to have similar kind of output. Only thing is, this g of j omega has to be calculated at this omega 1, whereas this g of j omega for the second signal has to be calculated at second signal's frequency, that is nothing but omega 2. Okay, so, and the phase angle is 3t, already is 3t input, and the phase angle that will be added with it is angle of g of j omega 2. Okay, so to find out this y1 and y2, we need the gain g of j omega 1 and g of j omega 2. We'll find out that. G of j omega at omega 1 is what we call it as g of j omega 1. And we already obtained the the closed loop transfer function as 5 by a square plus 6x plus 5 for k value of 5. And here, instead of s, I have to replace it with j omega 1. And if I put those values, this is what I get. Okay, so, and if I substitute the value of omega 1 is equal to 1 radians per second, I will get this complex number. This complex number, I can write it in polar form. So this is going to be the magnitude, and this is going to be the phase angle. So in the same way, I can find out g of j omega 2. It is nothing but g of j omega calculated at omega 2. So the same procedure applied. This is what I will get at the end, and this is its polar form. So both the magnitude and phase angle of g of j omega for the two different frequencies omega 1 and omega 2 have been found. So now, this is a LTI system, and therefore, I can use the principle of superposition. So principle of superposition is what is being explained here. If I take an LTI system and if I give an input R1 of t, and let me say this output is going to be Y1 of t, and similarly I'm going to give R2 of t as an input separately, and then if the corresponding output is Y2 of t, and then if I apply both the inputs R1 of t and R2 of t together, the output is going to be the individual sum of the individual outputs, that is Y1 of t plus Y2 of t. So for these two inputs applied together, this is going to be the total response. So we'll use that. Y of t is equal to Y1 of t plus Y2 of t, and Y1 of t is equal to magnitude of g of j omega. Magnitude of g of j omega is nothing but 0.69338. Okay, and similarly angle of g of j omega 1 is equal to minus 56.31. And similarly the magnitude of g of j omega 2 is equal to 0.27116, and the corresponding angle is minus 102.53. So you can just put those values. I've just substituted with the values. Already there is a phase shift of 10 degree, and along with this minus 56.31 degrees. So what I get is this is what? So this is the final response of the system for these two in this input which has got two components in it. So having done with the first subdivision, let us move on to the second subdivision. So for k is equal to 5 and 100, you need to find out the resonant peak and resonant frequency. So when k was 5, we found the natural frequency of oscillation omega n as 2.236 radians per second and damping ratio as 1.3416. We did it already. So if you look at this damping ratio, so the damping ratio what we have is 1.3416. Obviously, this is greater than 0.707. In the lecture number 3, you should have remembered that if the damping ratio is greater than 0.707, then the resonant peak is going to be 1. That means, so the maximum value will not exceed 1 at any frequency. So therefore, the resonant peak, that is the maximum value, is going to be 1. Resonant peak, MR is equal to 1, and or 0 decibels. And resonant frequency, the corresponding this one will be happening at omega r is equal to 0 radians per second. So that is what we understood. But when it comes to k is equal to 100, omega n is equal to 10 radians per second and theta is equal to 0.3, which is lesser than 0.707. And in that case, the resonant peak will be higher than 1, and it can be calculated using this expression. And similarly, the resonant frequency also can be, the corresponding resonant frequency also can be calculated using this expression. So since we have got omega n and theta, we can directly substitute those values in this expression and then get the corresponding resonant peak and the resonant frequency. Please note that resonant peak is always a dimensionless quantity unless it is converted to decibels using 20 log 10 of that value. So the third subdivision is also very straightforward. It is just finding out the bandwidth. Bandwidth also we have got a fixed formula, we have fixed expressions to calculate. It needs omega n and theta. And if you substitute those values, you will get this for k is equal to 5. And similarly for k is equal to 100, I can get this value. So why we were made to calculate all these specifications for two different values of k is equal to 5 and k is equal to 100 is just to understand for a prototype second order system, if the gain is increased, the resonant frequency increases, the resonant peak increases and also the bandwidth increases. The bandwidth increases means the cutoff frequency also increases. That could be observed from the figures. So in the first problem, we have understood to calculate the steady state sinusoidal response for an LTI system, especially when the input has got two components in it or two signals in it. And also we understood how to calculate the frequency domain specifications directly from the transfer functions. So the second problem is, as I said, it is to understand the correlation between the time domain and the frequency domain specifications. The problem what is given is the time domain response for a step input, and its steady state value is 2, and it reaches a value of 2.6 at the first peak. That is what we call it as the peak time. The time corresponding to this peak is what we'll be calling usually as peak time, and the corresponding value of this output is the peak value. Okay, so then peak overshoot is this distance over and above the steady state value. So what is the maximum value that has been attained by the response is what we call it as the peak overshoot. And apart from this peak overshoot, another time domain specification is also given, that is the rise time. How do we define the rise time? Time taken by the response to rise from 0 to the steady state value for the first time. The steady state value is 2. It reaches the steady state value of 2 at this 0.2 seconds, and therefore the rise time is 2. And the peak overshoot is given by this distance. Usually, this peak overshoot will be expressed as a percentage of the final steady state value. Okay, so this is what is given in the time domain response. The question is to find out the frequency domain specifications such as resonant peak and the phase margin. Okay, so it is obvious that to calculate the resonant peak and the phase margin, you need to know the value of zeta. Okay, so how do I get the zeta? I can make use of whatever data or whatever specification given in the time domain. How do we calculate the peak overshoot? The value of C at TP, peak time, that is a maximum value, minus the steady state value, C of infinity, that is the steady state value, expressed as a percentage or expressed in terms of the steady state value, that is 2.6 minus 2 divided by 2 is equal to 0.3. So that is the peak overshoot for this. But as I said before, to find out resonant peak and phase margin, you need zeta, and we can make use of this peak overshoot value to calculate the zeta. Especially the peak overshoot is related only to zeta, and therefore if I equate that value of zeta using the expression for peak overshoot, I will be able to get the value of zeta. So MP is e power minus zeta pi by square root of 1 minus zeta square, and that is equal to 0.3. So this exponential can be removed by taking a natural logarithm on both sides. Right side natural logarithm is ln of 0.3, and this since the natural logarithm also has got a base of e, this will be zeta pi by square root of 1 minus zeta square. So ln 0.3 is minus 1.2 basically, and since there is a negative sign here, this will become plus 1.2. And to find out zeta, you need to square on both sides. If we square on both sides, this will be pi square and this will be zeta square. So the denominator will be 1 minus zeta square, and the pi square can be brought to the other side, that is 1.2 the whole square divided by pi square is going to be 0.146. And again, if you do a little bit of simplifications, you will get this value of zeta. So once zeta is obtained, we can directly substitute those zeta value in the expressions of resonant peak and phase margin. Straight away, both these expressions doesn't require anything other than the damping ratio. Just substitute, you get the values. So please note that we have been asked to find out resonant peak and phase margin, which needs only the damping ratio, theta value. But sometimes it may be asked to find out the resonant frequency in addition to the resonant peak. So if you want to find out, the resonant frequency, you need to use this formula, this expression. So this expression uses both theta as well as omega n. But using this MP value, you will be able to calculate only the theta value. So to calculate omega n, you need another specification also. Usually the specifications of rise time or the peak time will be given. So you can use those specifications to find out omega n. For example, in this case, the rise time is given. So rise time expression is here, and from the peak overshoot, you would have calculated the theta value already, and you can put the same theta values here. And in that case, if you know the T or also rise time, if you substitute it by 0.2, then the only unknown in this expression is going to be omega n, which you can find. So once omega n is found, you can find out omega r using the values of omega n and theta. In the same way, sometimes you may be asked to find out the uh, bandwidth also. Bandwidth also needs both omega and theta for its calculation. So, so this completes the second problem. So in the second problem, we could understand how we can get the frequency domain specifications from the time domain specifications. In the same way, we can go from the frequency domain to the time domain also. In that case, probably you should start with this resonant peak, because resonant peak also depends only on theta. So use the value of resonant peak and get the value of theta first. Then probably you can use this resonant frequency expression to get omega n. So once theta and omega n are found, you can move from frequency domain to time domain also. So anyhow, whether it is from time domain to frequency domain or frequency domain to time domain, the connecting variables are theta and omega n. You should use appropriate specifications to find out the theta and omega n, and then you can move from one domain to another domain. Fine. So we'll move on to the third problem. So in the third problem, the open loop frequency response of a unity feedback system is given in a tabular form, not in a graphical form. Okay. And please note that it is given for open loop system. Maybe it is a closed loop system, but the frequency response is given for only the open loop system. Please, at this point, please note that all these frequency responses are mostly drawn for open loop systems, and from open loop system, we can find out the closed loop performance. Anyhow, those things we will study later. So, for this system, the open loop frequency response is given in the table. For different frequencies, the magnitude variation is given and the phase angle variation is also given. One more thing to be noted is the magnitude variation is given in actuals. They have not been transformed to decibels. Okay, yeah. The question is to identify the gain crossover, phase crossover frequencies, to evaluate the gain margin and the phase margin, and also to determine the change in gain record so that the gain margin of the system is 20 decibels. So before going into the problem, working out of the problem, let me just explain or recall, the specifications of gain margin and phase margin, and of course these crossover frequencies. So the gain crossover frequency is the frequency at which the gain crosses this 0 decibels. 0 decibels corresponds to 1, a gain of 1 in actuals. And similarly, the phase crossover frequency is the frequency at which the phase of the system becomes 180 degree, minus 180 degree. And the gain margin is the gain that could be added to the system to make the gain of the system at the phase crossover frequency as 0 decibels. And similarly, phase margin is the phase lag that could be added to the system to make the phase of the system as minus 180 degree at the gain crossover frequency. Okay, so let us use these principles to find out the solution for this problem. So the first thing is to identify the gain crossover and the phase crossover frequency. As I said, the gain crossover frequency is the frequency at which the gain becomes 0 decibels, or in actuals it is 1, the gain of 1. So if you look at, see here, the gain becomes 1, or if it is converted to decibels, it will become 0 at a frequency of 7 radians per second. So therefore, the gain crossover frequency omega GC is 7 radians per second. And similarly, the phase crosses minus 180 degree at 9 radians per second, and therefore the phase crossover frequency is equal to 9 radians per second. So it's very easy, straight away by observation you can find out. And the second part is to calculate the gain margin and the phase margin of the system. So as I said already, we need to find out what is the gain at the phase crossover frequency. At the phase crossover frequency, the 9 radians per second, the gain is 0.74. And if I convert it to, decibels, this is what I'm going to get. Okay, 0.74 converted to decibels. So please note that this is to the base of 10. And since the gain at this frequency, that is the phase crossover frequency, is minus 2.6254 decibels, if I want to make this gain as 0, then there is a provision that I can add another 2 plus 2.6154 decibels. So that means the gain margin of the system is 2.6154, because I can add another gain of 2.6154 decibels to the system, so that the total gain becomes 0 decibels. Okay, so the gain margin is this. And the phase margin, so at the phase crossover frequency, at the gain crossover frequency, that is this, the angle is going to be minus 169 degree. So the phase lag introduced by the system is minus 169 degree. And to make the phase lag as minus 180 degree, I can add another phase lag of 11 degrees. So it means that the phase margin is 11 degrees. So we completed the first two parts. The last part is the determination of the change in gain required so that the gain margin of the system is 20 decibels. If you look at the existing gain margin, it is 2.6154 decibels. Okay, it's a very small margin. Actually, this gain margins and phase margins are very much used in stability analysis. And smaller gain margin signifies that the relative stability of the system is very less. Also, the positive gain margin means that the system is stable, and the negative gain margin means that system is unstable. And the systems with lesser gain margin is less stable. Okay, even if it is positive, it means that it is less stable. So phase margin and gain margin are used as a measure to find out the on the relative stability of the systems. Anyhow, these topics will be dealt in detail in the future lectures, which will cover the topics on stability analysis. So the point is, since the gain margin is very, very small, the system can become unstable at any time due to the parametric variations or something in the system. So therefore, it is always good to have a larger gain margins. So how do we achieve a larger gain margin is by adding some gain, or by putting some more, inserting some more gain in the open loop system. So that is the question. So what we need to find out is to make the gain margin from the gain margin of the system as 20 decibels from a value of 2.6154 decibels. Okay, in that case, what is the change in the gain required? Okay, so that is the question. So obviously at the gain phase crossover frequency, the gain is 0.474, and converted to this is what we get. This is what we get. And if we need a gain margin of 20 decibels, that means at the phase crossover frequency, the gain should be minus 20 decibels. If the gain at the phase crossover frequency had been at minus 20 decibels, then the gain margin would have been 20 decibels. But now it is at minus 2.6154. So that means the magnitude plot has to be pushed down by minus 17.385 decibels. Okay, so that means to this value minus 2.6154, I should add another minus 17.385 decibels. So this is what is the the gain to be added to the system, and this gain is in decibels, but all the gains here is given in actuals. It is better to find out the actual gain to be how much the gain has to be changed. So if k is the actual gain, then how do we relate it? 20 log of k is equal to this much. That is whatever gain has to be added. So if you do simplifications, 20 can be brought to this side, and after the dividing this, then you can convert this logarithmic relationship into an exponential relationship. Now you get k. So this is how you should find out the actual value of k. So what we understand is the original gain has to be changed by a factor of 0.13512. So there was an actual gain of the system. With that actual gain, the original gain, the gain margin was only 2.6154, and if you change the gain by this factor, then the gain margin of the system will be the gain margin of the system will be 20 decibels. So in the third problem, we understood how to calculate or how to identify the gain crossover and phase crossover frequencies, and also the evaluation of gain margin and phase margin, and also the gain adjustment required to get a specified gain margin. So we understood how to solve three different problems. One on the steady state sinusoidal response and the frequency domain specifications, and getting the frequency domain specification from time domain specifications, or time domain specifications from frequency domain specifications, and also another problem on the gain crossover, phase crossover, frequencies, gain margin, and phase margin. So with this, we'll wind up this video. Thanks for watching.